The AVR is a Harvard architecture 8-bit RISC single-chip microcontroller which was developed by Atmel in 1996. The AVR was one of the first microcontroller families to use on-chip flash memory for program storage, as opposed to one-time programmable ROM, EEPROM, or EEPROM used by other microcontrollers at the time. The acronym AVR has been reported to stand for Advanced Virtual RISC, but it has also been rumored to stand for the initials of the chip's designers, ALF and VGRD RISC. Atmel says that the name AVR is not an acronym and does not stand for anything in particular. AVRs have a large following due to the free and inexpensive development tools available, including reasonably priced development boards and free development software. The AVRs are sold under various names that share the same basic core but with different peripheral and memory combinations. Compatibility amongst chips is fairly good. List of various features is shown on your screen. We will study most of them during this course. This course is designed to be used with our development-cum-learning boards like AVR LIP, EADT 4.0, EADT 5.0. Thus this course is a common tutorial for all products. Each of the hardware product is unique in its features. For example, AVR LIP is fully wired experiment platform for a Mega 32 microcontroller, whereas the EADT product family is fully unwired with multiple microcontroller support. This tutorial is generic one and can be used with any of our products. I have avoided the board-specific details in this tutorial. The knowledge you will gain from learning at Mega 32 microcontroller can be easily applied to a Mega 8 or any other AVR microcontroller with some modifications. You simply cannot use source code written for one microcontroller to other. Before you use it for other microcontroller, you will have to change the makefile values for MCU and also have to see if other technical details match. For example, a source code written for Mega 32 uses port A. This code cannot be used with Mega 8 as Mega 8 controller does not have a port A. You need to change the source code here. Mega 32 is available in 40-pin DIP package as well as in SMD package. Your screen displays a DIP package version. Mega 32 has 4 ports of 8-bit each. In simple words, Mega 32 has 32 pins to connect input and output, grouped as 4 ports. This diagram describes the connections for programming at Mega 32. Your experiment board is pre-wired with these connections. You need not to make these connections on the experiment board. This method of programming is called as in-circuit programming. It uses 4 pins, namely MOSI, MISO, SEK and RST. These 4 pins are connected to the ISP programmer. On your experiment board, these pins are hardwired. You may or may not use the XTAL pins as Mega 32 has built-in oscillator. Thus an external crystal circuit is not necessary. In future, if you decide to make your own application board, simply provide 5-volt supply between VCC and GND in addition to the connection facility to connect 4 pins of Mega 32 to your ISP programmer. You have to use a ISP programming software on your PC to program Mega 32. The diagram shown on your screen is a simplest form of input and output example. This will explain you as how Mega 32 handles its input and output. Imagine this application will make the LED on and off based for every key pressed by the user. Thus we have to accept the key input, process it and take action to on or off the LED. You have to configure pin PD0 as input pin and pin PD1 as output pin. AVR provides data direction register to configure it. Each port in AVR has 3 registers associated with it. For example, for port D, the name of 3 registers are port D, DDRD and pin D. The port D register is used for output, pin D is used as input and DDRD is used as configuration register to specify the usage of port pin as input or output. Here we want PD0 as input. Thus we have to specify 0th bit of DDRD as 0. The value 0 at any bit of DDRD configures respective pin of the port as input. Similarly, we want PD1 as output, so we have specified first bit of DDRD as high, which ensures that the PD1 will be output pin. Functions SBI and CBI used to set or clear value of particular bit of DDRD. This is a sample code for the application discussed in the last screen. Understand the use of SBI and CBI functions to set and clear values. Also look at the function monitoring switch press. This may not be a complete code. To complete the code you have to create a project, add .c file, add make file, add function definitions for SBI and CBI. You will also need to include header files. You should refer to sample source code provided.